Okay, so this is question 8 on the M2 paper Jan07. And we've got two masses hanging in equilibrium on a spring. So let me draw this out. Okay, so here's my spring, and then we've got two masses joined together, and the top mass A has a mass of 0.8 kilograms, and then mass B has a mass of 1.2 kilograms. We're told some information about the spring, which is that it has a modulus of elasticity of 49 newtons, and it's got a natural length of 0.5 meters. You guys off? Yeah. Okay, so part A is find the extension of the spring. Well, we can do that by it's in equilibrium, so the forces acting on it must there must be a net force of 0. So let me just draw the forces acting on this thing. Well, the force down, see John. So yeah, the force down is its weight, so that's going to be a total of 2 g down, and the force up is the force from the extension of the spring, and we can write that down as lambda over L x, where x is the extension. So this is going to be 49 divided by 0.5, which is 98. So this is 98x. There we go. Okay, so I just because it's in equilibrium, I just equate these two. So I've got 98x is equal to 2g. So x is equal to 2 times g over 98. Well, g is 9.8, so it's 9.8 over 98. So this is 2 times a tenth. So this is 0.2. So the extension is 0.2 meters. Now in part B, we're now asked to work out how much energy has been stored. What's the elastic potential energy in the spring? So to find the elastic potential energy, I just need to integrate the force with respect to dx, with respect to x, and the extension has been 0.2. So those are my limits. 0, it's extended from its equilibrium position 0 to 0.2, and this should tell me how much energy is stored in the spring. So this is the integration of 0.2 between 0.2 and 0, and the force, remember, was lambda over L, which was 98, and that's x dx. So I get 98 over 2 x squared when I integrate, and I'm going to sub in 0.2, and that gets me 49 times 0.2 squared, which gives me 1.96 joules. So now we're going to look at part C, and we've just worked out that there's 1.96 joules stored in the spring, and when block B, mass B, drops, then A is going to accelerate upwards past the spring's natural length and compress the spring by a distance x. So that 1.96 joules that's stored is going to get converted into different types of energy, and they're going to be gravitational potential energy, so write it like that, that's because block A is now risen risen by a certain distance, and so gain some gravitational potential energy. And there's also going to be some energy from the compression of the spring once it goes past its natural length. Now, we've got the total energy 1.96, and the gravitational potential energy gained is going to be mg times the height that it's been raised. And the height that it's been raised is going to be 0.2 meters, because that's how much the spring had been extended. So it's travelled up 0.2 to the spring's natural length, and then it's going to carry on a distance x, and that's how far the spring is going to be compressed. So that's mgh, that's the total height, 0.2 plus x. And then the energy from the compression, we've already worked out this expression, it's just 49x squared. So now I'm just going to multiply all this out. The mass now, because it's just mass A, is 0.8. So that's 0.8 multiplied by 9.8 multiplied by 0.2 plus x plus 49x squared. Okay, and I'm just going to tidy all this up. I've got 1.96 is equal to, now 0.8 times 9.8 times 0.2, I get 1.568, I think. And then I've got 0.8 times 9.8, and that gets me 7.84x, I believe, and then there's this 49x squared here. Okay, and then bringing this all over to one side, I get 49x squared plus 7.8 for x minus 0.392 is equal to 0. And then dividing this through by 49, I get x squared plus 0.16x minus 0.008 is equal to 0, which is what you're trying to show, and that's 5 marks. And then finally, to just solve it, it's just quadratic formula. So for part CII, we just say that x is equal to minus 0.16 x plus or minus the square root of 0.16 squared minus 4 times 1 times c, so that's going to be 0.008, and I've made that positive now, divided by 2 lots of 8, so that's 2. And you can work all that out, or if you're very lucky, you might have one of these nice calculators, and there is a way you can do it on here. So you go to mode, you go to equation, you pick the quadratic, which is option 3, and you put in your values of a, b and c. Well, a is 1 and b is 0.16 and c is negative 0.008, so I'm just going to cheat really, and press equals, and I get my 2x values. I've got 1 over 25 and minus a fifth. So the x values are 1 over 25 and x equals minus 1 fifth. Okay, now we just want one of those answers, and you should be able to see that just by thinking about the gravitational potential. We've taken, let's go up here, we said that x was extending 0.2 plus some distance past the equilibrium point, so it's this value of x that we want. Okay, so it's being compressed by 1/25 of a metre.